The next method of proof that we're going to learn about is called mathematical induction. Now, it's not to be confused with the term induction, which, if you've taken some philosophy courses, you may have heard this term. The type of induction that's talked about in philosophy is something different. This is mathematical induction, and we'll show many examples of using mathematical induction in a few different ways. So first, let's give an outline for what this type of proof looks like. So we start with the proposition, and the proposition will have the following form. We will say, for all n that is greater than m, s of n, meaning something is true, s of n is true for all n that is greater than m, where m and n are integers. That is, what it's saying is, what the proposition that we're trying to prove, what it's saying is that s of m is true, and s of m plus 1 is true, and s of m plus 2 is true, and dot, 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 dot. In other words, for every integer that is greater than m, greater than or equal to m, s applies to that integer. Now, s could be anything. S could be any type of sentence. Okay, now, typically, m is equal to 0 or m is equal to 1. So typically, it's going to be something like, for all integers n greater than 0 or greater than 1, something applies to those integers. So we'll see many examples of this. And so again, this is a proposition that is making a claim about an infinite number of integers. It's making a claim that it's true, that it claims it's true for m and m plus 1 and m plus 2 and forever to infinity. Okay, so it's making a claim about an infinite number of integers. We have to prove that. That should seem at first that it's impossible to do. How can we prove that something applies to all integers, right? But we've seen proofs where most of the proofs that we've done, we've shown that things apply to all integers or to all well, not to all. Well, here we're not trying to prove. Well, we prove things for all integers. Here we're not proving for all integers. We're specifically proving for all integers that are greater than or equal to m. Okay, so the proof is going to look like this using mathematical induction. We're going to have two parts. Part one is we're going to call the basis step, and that's going to be the easy part. Okay, so part one is show that s of m is true. In other words, show that this thing is true for the beginning, for m. Show that s of m is true. That's the basis step. Whoops. Step two, we'll call the inductive step. In the inductive step, what we're doing is the following. What we want to show is that for every integer k that is greater than or equal to m, we want to show that if s of k is true, then s of k plus 1 must be true as well. Okay. In other words, we're showing that if we know s of k, then it must be the case that s of k plus 1. Now, we're going to see that these two steps together will prove the proposition. It helps to think of an analogy, and there are actually two analogies that are common to use here. So one is the dominoes analogy. So the idea is like this. I want to prove an infinite number of statements. I want to prove S1, S2, S3. Here, we're starting from 1. We could really start from 0, or we can start from 3, or we can start from -2, whatever. But typically, we start from like 1 or 0. So let's say we have S1, NS2, NS3, NS4, all of these things that we want to prove. S6, SK plus 1, SK plus 2, right? K is any random natural number. And, so we want to prove all of these statements. So you can think of them as lined up like dominoes, statements lined up like dominoes. Now, the basis step is we show that the first statement falls, meaning the first statement is proved true. The first domino falls. We show that s of 1 is true. That's the basis step. Then the inductive step is we show that whenever the kth domino falls, that this causes the k plus 1th domino to fall. Meaning for every possible value of k, if domino number k falls, then domino number k plus 1 will have to fall as well. That's what we're going to prove in part 2. Now, taking part 1 and part 2 together, so we know that the first domino falls. And we know that whenever a single domino falls, the next one will also have to fall, right? Whenever domino number k falls, then domino number k plus 1 falls. The result, the conclusion is, then all must fall, meaning all statements are proved true. Again, why? Because we know the first one falls. So therefore, well, if the first one falls, then the second one has to fall, because whenever domino number k falls, then domino number k plus 1 also has to fall. So if S1 falls, then S2 has to fall too. But if S2 falls, then by the same reasoning, S3 also has to fall. But if S3 falls, then by the same reasoning, S4 has to fall. And we can keep chaining this reasoning again and again and again. So this proves that all dominoes have to fall. So we're going to have the same idea for numbers. Okay, so for integers. Here's another analogy, the ladder analogy. So if I want to prove that I can climb up to the top of the ladder, maybe it's even an infinite ladder, right? So I have steps on the ladder: step 1, step 2, step 3, step 4, ... So suppose I know that I can reach step 1. Okay, so I can get onto step 1. And then suppose I know that whenever I am on step k, I am able to get from there to step k plus 1. Right, so I can reach step k plus 1 if we reach step k. As a result of these two things, again, as a result of knowing that I can reach step 1, and that if I can reach step k plus, that I can reach step k plus 1 if I can reach step k, as a result of those two things, I can know that I can get all the way to the top of the ladder, as high as it is, because I know I can start climbing the ladder, and I know that whenever I am on step k, I can go to the next step. I can go to step k plus 1. So that tells me that I have a way of getting to the top, all the way to the top, as high as it might be. So that's the idea of mathematical induction. Now let's do some examples. So the first two examples that we're going to do will involve summations. So this is, we talked about in the first week or two of the semester, the summation notation. So you can go, if you're feeling rusty about that, you can go review that. So we're going to use it. We're going to use that notation in the next two examples. And then we'll do other types of examples. So here's the proposition. It says that the sum of the first n odd natural numbers is n squared, is equal to n squared. So if I take the first n odd natural numbers, so what are natural numbers? That's 1, 2, 3, and so on. If I take the first n odd natural numbers and I add them up, the proposition claims that that sum is going to be n squared. Let's first do some examples to make sure we understand what the proposition is saying. Okay. So for example, let's say n is equal to 1. So what is that saying? The sum of the first 1 natural numbers. So if I just take the first odd natural number. So the sum of the first 1 odd natural numbers is just 1, because I just have that one number. 1 is the first odd natural number, and I just take that number, don't add it with anything else. It's just that number by itself, it's 1, which is equal to 1 squared. So in other words, n squared, right? So the sum of the first 1 odd natural numbers is 1 squared, right? So it works for n equals 1. Okay. How about for n equals 2? So what does the proposition say when n equals 2? Well, it says the sum of the first 2 odd natural numbers is, well, it's 1 plus 3, okay, which is equal to 4, which guess what is equal to 2 squared. So the proposition seems to work for n equals 2. How about n equals 3? The sum of the first 3 odd natural numbers is, so the first 3 odd natural numbers, so there's 1, that's an odd natural number, not 2. The next odd natural number is 3, and then 5. So the sum of those 3 odd natural numbers is 9. which is equal to 3 squared, right? So these are a few examples. Of course, these examples do not prove the proposition at all. They just show that it works in 3 specific cases, but we have to prove that it works in all cases. Let me just give you another example. Let's say n is equal to 17. So what does the proposition claim? I'm not going to verify it. I'm not going to verify this, but I'm going to just explain what does the proposition claim for when n equals 17. Well, the proposition claims that the sum of the first 17 odd natural numbers, I don't know what those are even, and I certainly don't know what the sum is, but the proposition claims that that sum should be equal to 17 squared. Again, I don't yet know that that's true, but that's what I want to prove. I want to prove not just 17. I want to prove this for every possible number of odd natural numbers, right? And any basically 1, 2, 3, 4, any amount of natural numbers. How about for n equals 25, right? So I want to prove this as well. I want to include in my proof to cover n equals 25. According to the proposition, the sum of the first 25 odd natural numbers should be equal to 25 squared. So again, we haven't proven this, but this is what the proposition is telling us. Okay, now we hopefully understand what the proposition is saying. Now, what I want to do is convert this proposition into more mathematical symbols. So the way it's written the way it's written originally is as an English sentence, basically. But I want to convert it to a more mathematical expression so that it will be easier for us to work with in the proof. So this, again, the proposition says the sum of the first n odd natural numbers is n squared. That is, for every integer n that is greater than or equal to 1, if you take the first n natural numbers, well, what are the first n natural numbers? Well, the first one is 1, then 3, then 5. So 1 plus 3 plus 5 plus 7. The nth odd natural number will be 2 times n minus 1. Okay, so again, this is the first odd natural number, second odd natural number, third odd natural number, fourth odd natural number, dot, 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 the nth odd natural number. Okay, so the proposition claims that this sum is equal to n squared. And the sum of the first n odd natural numbers is n squared. Here's another way to write it. That is, for every integer n that is greater than or equal to 1. So let's just rewrite this. So what is 1? 1 is 2 times 1 minus 1. 3 is 2 times 2 minus 1. 5 is 2 times 3 minus 1. 7 is 2 times 4 minus 1. Plus dot, 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 plus 2n minus 1. Right, notice the pattern here. The first odd natural number is 2 times 1 minus 1. The second odd natural number is 2 times 2 minus 1. The third odd natural number is 2 times 3 minus 1. The fourth odd natural number is 2 times 4 minus 1. The nth natural number is 2 times n minus 1. Okay, so the proposition claims that this sum, again, the sum of the first n odd natural numbers is n squared. Let's rewrite this using summation notation. So that is, for every integer n that is greater than or equal to 1, the sum from I equals 1 through n of 2 times I minus 1 should be equal to n squared. The proposition claims that it is equal to n squared. All right, so let's see. This is 2 times 1 minus 1. So this is when I is equal to 1. So it's 2 times I minus 1, 2 times 1 minus 1. Then plus 2 times 2 minus 1. Then plus 2 times 3 minus 1. Then plus 2 times 4 minus 1. Plus dot, 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 plus 2 times n minus 1. Right, so this summation notation expresses this. Okay, and the claim of the proposition is that this sum should be equal to n squared. Now, this is the thing that we're trying to prove, S of n, right? Remember the form of the proposition. This is just, it's just I guess you can say an open sentence, right? An open sentence that says that the sum from I equals 1 through n of 2 times I minus 1 equals n squared. we want to prove that this is true for every integer n that is greater than or equal to 1, right? So remember, that's the form of a statement that we're going to use induction for, right? The form of a statement that we want to prove using induction is going to always be something like, for every integer n greater than or equal to 1 or greater than or equal to 0 or something like that, for every integer n greater than or equal to something, s of n. That s of n applies to every integer n that is greater than or equal to 1 or greater than or equal to 0 or whatever it might be. Okay, so now we're going to prove this using induction, right? So far we were just rewriting the proposition in a way that will make it more amenable to proving using induction. So again, just rewrite. Here's the rewritten proposition. For every integer n that is greater than or equal to 1, the sum from I equals 1 through n of 2 times I minus 1 is equal to n squared. That's what we want to prove. So we're going to prove this by induction, and we're going to start with the basis step. Now, what should we look at in the basis step? Well, what we look at is the lowest possible value of n. So here, we're talking about n being greater than or equal to 1. So the lowest possible value of n is 1. So we're going to look at what happens when n is equal to 1. So when n is equal to 1, what do we have here? What is the sum? What does the sum become? So we have the sum from I equals 1 through n of 2i minus 1. Well, n is equal to 1, so we have the sum from I equals 1 through 1 of 2i minus 1. That is just 2 times 1 minus 1, which is equal to 1. Okay. And now we have to check that it is in fact equal to n squared, right? What we were doing until now was just this. Okay, but we have to check, is the proposition true for n is equal to 1? So in other words, does this align with n squared? Well, let's see. It does. It agrees with n squared, because n squared is, in this case, it's 1 squared, which is equal to 1. So we have, again, this 1 is equal to this 1. So that's great. Okay. So that's the end of the basis step. What do we do in the basis step? We show that it is true for the lowest possible value of n, which in this case is 1. So we show that the proposition works, right? This formula works for n is equal to 1. Now we have the hard part. Okay, so far what we had was the easy, quote unquote, easy part. Now we have the hard part, which is the inductive step. So let's first write out clearly what we want to accomplish in this step. So again, we're still continuing the same proof. We're just now in the second part of the proof. So what we need to do is the following. We need to show that for every integer k that is greater than or equal to 1, we need to show that if s of k, then s of k plus 1. Meaning, if the sum from I equals 1 through k of 2 times I minus 1 is equal to k squared, then we are forced to say that the sum from I equals 1 through k plus 1 of 2i minus 1 should be equal to k plus 1 squared. So again, we want to prove that if s of k is true, then s of k plus 1 must be true as well. And we need to prove that that works for every integer k that is greater than or equal to 1. So whatever reasoning we use will have to apply to every integer that is greater than or equal to 1. So this is what we want to prove. Again, we want to prove an if-then kind of statement. So, thinking back to direct proof, how do we prove an if-then statement? Well, we suppose that this is true, right? And then we show that from there, it follows that this must be true as well. Okay, so we start. So this is what we want to prove. And here's how we'll show it. We suppose that this part is true, right? We suppose that this is true, right? The sum from I equals 1 through k of 2 times I minus 1 is equal to k squared. And notice here, the I equals 1 and the k are not written, they're not written below and above. They're written a little to the side, but that's fine. It's just a little, got a little squeezed in over there in the slide. Okay, so suppose that is true. Again, we have to show that if we suppose this is true, then it must follow from there that this has to be true. Okay, so suppose that the sum from I equals 1 through k of 2i minus 1 is equal to k squared. Well, then, what is the sum from I equals 1 through k plus 1 of 2i minus 1? Again, we're trying to prove something about the sum from I equals 1 to k plus 1. So let's see. Let's figure out what is it? What is it? What is it equal to? Well, let's write it out. Let's expand the sum. So we have, well, let's see, 2i minus 1. Right? So when I is equal to 1, we have 2 times 1 minus 1. So that's 1. Then we have 2 times 2 minus 1. So that's 3. Then we have 2 times 3 minus 1. That's 5. Dot, 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 dot. And then what happens when I is equal to k? Well, then we have 2 times k minus 1. Then what happens when I is equal to k plus 1? Remember, that's the last possible value of I for this particular sum. What happens when I is equal to k plus 1? Well, you have 2 times I minus 1. So you have 2 times k plus 1 minus 1. Okay, so that's this sum here. But now notice something here. Notice that this thing here, yes, just 1 plus 3 plus 5 plus dot 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 plus 2k minus 1, that's actually equal to this sum. Right? Think about it. Okay, so let's rewrite this, right? So this is equal to the sum from I equals 1 through k of 2i minus 1. And then, of course, plus this 2 times k plus 1 minus 1 from before. But now here's where we really go to the next step, because which is as follows. We are supposing that the sum from I equals 1 through k of 2i minus 1, right? We're supposing that this sum is actually equal to k squared. So that means, again, this sum can be replaced with k squared. That's just like this. So this becomes k squared. And then let's expand this. So we have 2 times k, so that is 2k. Then we have 2 times 1, so that's 2. And then we have minus 1. So again, k squared plus 2k plus 2 minus 1. If we simplify that a drop, we have k squared plus 2k plus 1. Now, our goal is to show that this sum, well, our goal is to show that the sum from I equals 1 through k plus 1 should be of 2i minus 1 should be equal to k plus 1 squared. So we are trying to show that this thing is equal to k plus 1 squared. So can we show that this is equal to k plus 1 squared? Well, if you remember factoring, it should be fairly easy. Right? We can factor this just like this, k plus 1 squared. Right? K plus 1 squared is equal to k squared plus 2k plus 1. So what have we shown? Well, we've shown that by supposing that this if part is true, by supposing that s of k is true, that leads to the conclusion that s of k plus 1 is true, right? It leads to the conclusion that s of k plus 1 is true. Again, if we suppose that the sum from I equals 1 through k of 2i minus 1, if we suppose that the sum from I equals 1 through k of 2i minus 1 is equal to k squared, then we are forced to conclude that the sum from I equals 1 through k plus 1 of 2i minus 1 is equal to k plus 1 squared. So again, we have proven this if-then statement, that if the formula works for k, then it has to work for k plus 1. So that's the end of the inductive step, because that's what we're trying to prove in the inductive step. Again, the goal of the inductive step is to show that if s of k, then s of k plus 1. And that's what we've done. So since we've done the basis step and the inductive step, we have completed the proof. Okay, now I want to go and give you a further give you a little bit of justification for our reasoning here, right? It doesn't seem, at least at first glance, that our reasoning is solid. Like, so here I'm going to try to give you some justification for the type of reasoning that we were doing here. So for example, how do we know that the proposition is true for n equals 17? Okay, well, that is, how do we know that the sum from I equals 1 through 17 of 2i minus 1 is actually equal to 17 squared? In other words, how do we know s of 17? Well, here's the thing. We have proved two things in the proof that we just did. We have proved two things. Number one, we have proved that S of 1 is true, right? We've shown that the proposition works for n equals 1. So we've shown that S of 1 is true. We've also shown that for every integer k that is greater than or equal to 1, if S of k, then S of k plus 1, right? If the proposition works for k, then it has to work for k plus 1. That's what we showed in the inductive step. So now putting these two things together, we can reason as follows. We know that S of 1 is true. We proved that. Well, for every integer k, if S of k, then S of k plus 1 is also true. So if we have S of 1, it means we also have S of 2, because that's the next number. That's k plus 1. But again, this thing is not limited to 1. This is applying to every integer k that is greater than or equal to 1. So therefore, if we know S of 2, then using that same reason, we also know S of 3. But if we know S of 3, then by that same reasoning, we know S of 4. By that same reasoning, we know ... all the way through S of 16. And if we know S of 16, then we know S of 17. So that's how we know that S of 17 is true. But of course, this type of reasoning is not limited to 17. It works for every positive integer. For example, how do we know that S of 33 is true? Right? How do we know that the sum from I equals 1 through 33 of 2i minus 1 is equal to 33 squared? How do we know that? Well, same reasoning. We know S of 1 is true. We prove that. If S of 1 is true, then S of 2 must be true. If S of 2 is true, then S of 3 must be true. If S of 3 is true, then S of 4 has to be true, all the way through S of 32. If S of 32 is true, then S of 33 has to be true. Right, so this, and of course, that's not limited to 33. This type of reasoning works for every integer that is greater than or equal to 1. It works for every positive integer. So that's the justification behind the mathematical induction. All right, let's do another example involving sums. So here's the proposition. It says if n is a non-negative integer, then the sum from I equals 1 through n of I times I factorial, okay, this sum is equal to n plus 1 factorial minus 1. Now, how did someone come up with this proposition? That's not our business. We're not worried about that. We're not in the game of coming up with propositions. We're just in the business of proving propositions. Okay, so we have to prove this. We're given this proposition, it's a claim, we want to prove it. So we're going to use induction, and we're going to start with the basis step. But now, what should be the where do we want to start here for our basis step? In other words, in the basis step, what is going to be the value of n? Well, here the proposition claims that this is if n is any non-negative integer. So the lowest possible value of n, we always start with the lowest possible value of n. So that would be 0. 0 is a non-negative integer. It's the lowest possible non-negative integer. Okay, so when n is equal to 0, what we have is, well, what is this sum equal to? We have the sum from I equals 0 through n of I times I factorial, which is the sum from I equals 0 through 0 of I times I factorial, which is 0 times 0 factorial, which is 0 times 1, which is equal to 0. Now, so that's the sum. Now we want to check to make sure that it is equal to this, right? Because the claim is that this sum should be equal to this. Well, let's check that out. Well, it does. It agrees with n plus 1 factorial minus 1, which is 0 plus 1 factorial minus 1, which is 1 factorial minus 1, which is 1 minus 1, which is 0. So these align, these agree with each other. So that's good. So that's the basis step. In other words, we have proven that the proposition works when n is equal to 0, meaning the lowest possible value of n. Okay, that's the basis step. That's the easy part. Continuing the proof, we have the inductive step. Here, what we need to do is we need to show for every integer k that is greater than or equal to 0, we need to show that if the sum from I equals 0 through k of I times I factorial is equal to k plus 1 factorial minus 1, then the sum from I equals 1 through k plus 1 of I times I factorial should be equal to k plus 1 factorial minus 1. That's what we want to show. So here's how we'll do it. Suppose that the if part is true, right? Suppose that the sum from I equals 0 through k of I times I factorial is equal to k plus 1 factorial minus 1. We have to show what happens. We have to show that the sum from I equals 0 through k plus 1 of I times I factorial is in fact equal to this. Okay, so let's figure it out. What is this sum? Let's write it out. So we start from I equals 0. So we have 0 times 0 factorial plus 1 times 1 factorial plus 2 times 2 factorial plus ... plus k times k factorial plus k plus 1 times k plus 1 factorial, right? Because this sum is going through k plus 1. Okay, great. Now notice that this is actually equal to this. Right? It's the sum from I equals 0 through k of I times I factorial. That is this. So we can rewrite it as follows. Right? So we have the sum from I equals 0 through k of I times I factorial, and then of course plus this thing from the end. So that's what we put in here. But now we are supposing that this sum, the sum from I equals 0 through k of I times I factorial, is in fact equal to k plus 1 factorial minus 1. So let's rewrite it like this, right? This sum becomes just k plus 1 factorial minus 1. And then we have the k plus 1 times k plus 1 factorial from before. Now, the next thing to realize is, well, we are trying to get to a form. We're trying to prove that this sum here, right, the sum from I equals 0 through k plus 1 of I times I factorial, we're trying to prove that it is equal to this, k plus 1 factorial minus 1. So I want to combine these factorials together, if possible. Well, what I'm going to do here is factor. So here we have a term that is just k plus 1 factorial. Really, it's 1 times k plus 1 factorial. Okay, here we have k plus 1 times k plus 1 factorial. So here we have a common factor. Again, k plus 1 factorial, and then here also we have k plus 1 factorial. Here we have k plus 1 factorial being multiplied by 1, and here we have k plus 1 factorial being multiplied by k plus 1. So I can factor it as follows: 1 plus k plus 1. So again, the 1 from here, right? It's 1 times this. That's 1 plus the k plus 1 times the factorial. So it's again 1 plus k plus 1 times the factorial, and then of course we can't forget about the minus 1. So we have minus 1 outside. Okay, now let's just simplify this for a second. So that is k plus 2 times k plus 1 factorial minus 1. Now, what is this? So k plus 1 factorial means you start from k plus 1, then multiply by k, then k minus 1, and so on, all the way down to 3 times 2 times 1. And then here we have at the beginning, multiply it by k plus 2. Well, guess what? That is just, so this whole thing, yes, this whole thing just becomes k plus 2 factorial. And then we still have the minus 1. Now this k plus 2 can be written as k plus 1 plus 1. So we have k plus 1 factorial minus 1. And that's what this sum is equal to. But that's exactly what we're trying to prove. We were trying to prove that if the sum from I equals 0 through k is this, then this, right? So what did we do? We supposed that the sum from I equals 0 through k is this. And what we got is that the sum from I equals 0 through k plus 1 of I times I factorial is actually equal to this. In other words, it's actually equal to this. So we completed the inductive step. And therefore we completed the proof.